Okay, so we need to estimate the values of phi, mu0, mu1, and sigma, the covariance matrix, and we do that using maximum likelihood. As we have seen before, it is better to maximize the logarithm of the likelihood, and we need to do the same here. So when you maximize this probability distribution of this likelihood, what we get in the end is these formulas. So we see here, to compute phi, all you need to do is consider all the examples you have available, like in this case, all the animals that you have available for training your model, all your dogs and your elephants. Suppose that we have in total 1,000 animals. Then all you need to do is check how many of these 1,000 are has the label 1 for elephant. So suppose that out of these 1,000 animals, 500 are elephants. So you will sum 1 for each of the animals, for each of the elephants, so you will have 500, and then you just need to divide 500 by 1,000. And what you are going to get is 0.5. So that's the probability that if you take an animal from your data set, you will get an elephant, which in this example is 0.5. Okay. In the case of the mean vectors, you need to compute a mean vector of dogs and a mean vector for elephants. So what this formula is telling us is that you need to go over all your set of animals, your 1,000 animals, and check the label of each of these animals. If the label is 0, then you take the input vector for that animal, so the height and the tail size, and you will sum that vector to the next vector, which will be the vector corresponding to the next animal that has also a label of 0. So basically what you are doing here is take all the animals that are dogs and sum its corresponding vectors. Okay, so you will sum all the heights of the animals, of the dogs, and all the lengths of their tails. You will sum all these values. Okay, and then you will divide this vector containing the sum of the heights and the sum of the tails. You will divide it by the number of elephants, of dogs, sorry. So in this case you will divide it by 500. Then you will do the same, but for elephants you will take all the input vectors corresponding to elephants. You will sum all of the weights, and you will sum all of the lengths of the tails, and then you will divide both by 500. Okay, so that's what this denominator is telling you. Sum one for each of the elephants that you have, and here it is telling you sum 1 for every dog that you have. So once you have done that, you will have the vector that is like the average of the heights and the lengths of the tails of the dogs, and the same for elephants. And finally, you need to compute the covariance matrix for this data set. So here the formula, this is the standard formula for computing the covariance matrix. Here this x is a vector column, this mu is another vector, and when you subtract this you will have a column vector. You will take that column vector, you will transpose it to generate a row vector, and when you compute this product, column times a row vector, you will get a matrix. So if these vectors are of size 2, for example, for 2 variables, height and tail, then the result of this operation is that you will have a matrix which is a square, and in this case is of dimension 2, because we are considering 2 features. If you were considering, for example, 10 features, then the covariance matrix will be a 10 by 10 matrix, a square matrix. Now, you should pay attention to the index. So I is the index that goes over the number of examples, from example 1 to example m. Okay, and this subindex here is telling you, okay, for an example I, you need to subtract the mean vector of the corresponding mean vector for that example. So you need to check for, if you are considering example 1, I equals 1, you will need to check what is the label of example 1. If the label is 0, then you need to subtract here mu 0. But suppose that you are in example 200, I equals 200, and the label for example 200 is a 1, then here you will subtract mu 1. So this is just a way to code which of these two means you need to subtract. And the idea is, if you are considering here an example of an elephant, you need to subtract the mean of the elephant. If you're considering an example here that is a dog, then you need to subtract the mean vector of the dog, because it doesn't make sense to have a dog here and subtract the mean of elephants, or vice versa. So this Gaussian discriminant analysis model, or the algorithm for this, is basically generating these 4 parameters, which consists simply in checking every example and count these numbers and compute these fractions here. Because once you have that, then you can apply these probabilities, and these probabilities are the ones that you need for applying the base rule, which is this one here. Okay, so in this case the learning algorithm consists in computing just probabilities, and specifically computing these parameters phi, the covariance matrix, the mean vector for 0, and the mean vector for 1. Now this Gaussian discriminant analysis model has an interesting relationship to logistic regression. If we view the quantity probability of y equals 1 given some input vector x and these 4 parameters as a function of x, so if we see this probability as a function of x, we'll find that it can be expressed in this form: 1 over 1 plus the exponential of the negative of the dot product of the parameters and x. Okay, where theta is some appropriate function of the parameters that we specified here. And this is exactly the form that logistic regression used to model the probability of y equals 1 given x. Why is that? Because in the Gaussian discriminant model, in the formula for the normal distribution, we have some exponential there, and you can transform that formula to get something similar to this one. So if the probability of x given y is a multivariate Gaussian, then the probability of y given x necessarily follows a logistic function. Okay, so if our data behaves as a normal distribution, or can be explained using normal distribution, and we compute this Gaussian distribution discriminant analysis, then inherently we are solving a logistic function. But the converse, however, is not true. So if you apply logistic function, this does not imply that the probability that you are computing is a multivariate Gaussian. Okay. So GDA makes a stronger modeling assumptions and is more data efficient. It requires less training data to learn well when the modeling assumptions are correct, or at least approximately correct. So what this is telling us is that if your data really behaves as a normal distribution, then it is better to use GDA over logistic regression, because GDA exploits this information, exploits the fact that the points behave as a normal distribution. And logistic regression makes weaker assumptions and is significantly more robust to deviation from modeling assumptions. So if you can see that your data is not behave as a normal distribution, then it is better to use logistic regression, because it is more robust, because logistic regression doesn't make any assumption about the probability distribution of the points. It just simply tries to minimize a classification error. So specifically, when the data is non-Gaussian, then in the limit of large datasets, logistic regression will almost always do better than GDA. So the message is, if your data is Gaussian distributed, use GDA. If not, use a logistic regression. Now I will talk about some specific points regarding decision theory that is very useful to know when we are implementing classifiers. So suppose that we have an input vector x together with a corresponding vector t of target variables, and our goal is to predict t given a new value for x. For regression problems, this t will be a continuous variable, okay, for regression, and in classification this t will be, or will represent a class, just a label. The joint probability distribution of x and t provides a complete summary of the uncertainty associated with these variables. So if we can estimate this joint probability distribution of all the possible combinations that of values that x can take and t can take, this probability distribution, this joint probability distribution, will or can be used to derive probabilities of some values taken by x and some values taken by t. Determination of this joint probability distribution from a set of trained data is an example of inference, and is typically a very difficult problem in the general case. So in the previous model, GDA, we did something like this for a specific case where the data behaves Gaussian. In a practical application, however, we most often make a specific prediction for the value t, or more generally take a specific action based on our understanding of the values of t. And this aspect can be analyzed using decision theory. Okay, so one thing is to compute what is the most probable label, like whether it is a dog or whether it is an elephant. But once you have this information, this probability, you have to make a decision, which is doing an action in the real world. And how are you going to make the decision about the action that should be taken? That can be analyzed using decision theory. So consider, for example, a medical diagnosis problem in which we have taken an X-ray image of a patient, and we wish to determine whether the patient has cancer or not. Okay. In this case, the input vector x is the set of pixels in the image. The output variable t will represent the presence of cancer. So we can consider two classes, class 1, and this class 1 would represent that the patient has cancer, and class 2 will denote when the patient does not have cancer. Okay, so C1 is cancer, C2 is non-cancer. We might, for instance, choose t to be a binary variable such that t equals 0 corresponds to class 1 and t1 corresponds to class 2. The general inference problem then involves determining the joint distribution what possible values X can take, so the pixels of the images, what values can take, and what is the probable classification of that image. And this will give us a complete probabilistic description of the situation. Although this can be a very useful and informative quantity, in the end we must decide, we need to take an action, either to give a treatment to the patient or not. And we would like this choice to be optimal in some appropriate sense. We shall see that the decision stage is generally very simple, even trivial, once we have solved the inference problem. So the main difficult part is to be able to estimate this probability distribution, which is a joint probability distribution. Once we have done that, and once we have decided how we are going to use the probabilities to make a decision, and then the problem is simple. So we are interested in the probabilities of the two classes given the image, which are given by this conditional probability. The probability that the classification is K given the image of the patient, and we'll do that using the Bayes rule, okay, which is the same that we saw before. Note that any of the quantities appearing in Bayes theorem can be obtained from the joint distribution, probability of X and Zk, by either marginalizing or conditioning with respect to the appropriate variables. So when you have a probability distribution, a joint probability distribution, this can be written in this way. For example, using a conditional rule. This will correspond to the second option here, the conditioning. So you can say, for example, the probability of X given C times the probability of C. Or you can also choose the other way around, like the probability of C given X times the probability of X. Okay, this is one way to do it, and the other way is to marginalize the probability functions. So for example, if you want to get to the probability of X from this joint probability, you will need simply to give all the possible values to this variable here, and you will sum all the possibilities, and then what you are doing is marginalizing C, and you can simply delete C from this joint probability, and by doing that you can get the probability of X, and also you can do, if you marginalize X, you can obtain the probability of C. So these two probabilities, the conditional probability and the marginalized probability, can be computed from the joint probability distribution. So what we want to do is to minimize the misclassification rate. We want to make the less number of errors. So suppose that our goal is simply to make as few misclassifications as possible. A mistake occurs when an input vector belonging to class C1 is assigned to class C2, or vice versa. A rule will divide the input space into regions Rk, which are called decision regions, one for each class, such that all points in region K are assigned to class K. So the probability of making an error can be written like this. The probability of making a mistake will be the probability that some X that is in region 1 is classified to be class 2. And the other kind of error is the probability that some X that belongs to region 2 is finally classified as being in class 1. So this is the way in which we can compute the error of our model. From the product rule of probability, we have that we can write this, the probability of Ck given X times the probability of X, and therefore the minimum probability of making a mistake is obtained if each value of X is assigned to the class for which the posterior probability is largest. Okay, so we will consider this as a way to assign points to some class. For many applications, our objective will be more complex than simply minimizing the number of misclassifications. Let us consider again this medical diagnosis problem. We know that if a patient does not have cancer and we incorrectly diagnose as having cancer, the consequences may be that the patient get scared because you are saying that she has cancer when she's not really sick. Okay, but later more research will tell you that it was a mistake and she is fine. Okay, this is a problem, but let's say is the smallest problem. The other case is that the patient is sick and you classify or diagnose this patient as healthy. Then the problem is that the patient will just go away thinking that she is healthy and she could have some premature death due to lack of treatment. So both are mistakes, but this second one is the worst. So we can consider this importance, relative importance of the mistakes, to reduce our risks in doing such big mistakes. So since this the consequences of these two types of mistakes can be dramatically different, it would clearly be better to make fewer mistakes of the second kind, even if this was at the expense of making more mistakes of the first kind. So we can formalize this through introduction of a loss function, also called a cost function, which is a single overall measure of loss incurred in taking any of the available decision actions. So our goal is then to minimize this total loss incurred. The way you do that is using a matrix like this one. So here what you're saying, if a patient that has cancer is classified as having cancer, then that is correct. So you don't need to pay any loss. You don't have any loss here because you did it correctly. Also, if your patient is healthy and you classify the patient as healthy, then also you did it correctly and then you don't have any loss. But if you have a patient that is normal and you diagnosed this patient as having cancer, that's a mistake, but is the less important mistake. You will have a loss only of 1 unit. And in the second kind of mistake, if a person has cancer and you say that the person is normal, then this will have a huge loss. So you will have a 1000 here. So this matrix can be computed and stored in some variable L, and then you can use that information to minimize the error. So our goal then is to choose the regions Rj in order to minimize the expected loss, which implies that for each x we should minimize this product here. So what you would do is take one example, use your probability distribution to say what is the most probable case, and if you classify that for the case of k, you will multiply this or weight this probability by the loss if you make this error, and you will need to compute for every possible class. So in the end, the final decision will consider not only the probability but also the cost related to making an error for that example. As before, we can use the product rule to eliminate the common factor. So in the same way we explained before, we don't really need to compute the denominator. We can simply compute the product here if we just want to have a score to make a decision. Thus, the decision rule that minimizes the expected loss is the one that assigns each new x to the class J, for which the quantity, this quantity here, is a minimum. So this is particularly important to know this kind of techniques, especially when you are in the medical domain, because in those situations different mistakes can have different importance, and you want to maybe your model to make more emphasis in some specific mistakes, even if the other kind of mistakes is increased in the number of instances that you make these mistakes. So this was all about generative models, Gaussian discriminant as a specific generative model, and some bit information about the decision theory that is more relevant for classifiers. I hope this is useful. Thank you guys, and talk to you later.